So before we move on to that handout that you have in front of you, what do you know about Ferris wheels? That's really too bad there aren't more people here today. It would be nice to have more input. What do you know about Ferris wheels? Has anybody ever been on one? No? Yes? Been on other rides though, like Ferris wheel? I'm going to need some input from you. What do you know? Like, somebody explain what a Ferris wheel is or something like that. Yeah, spins. What else? Huh? Yeah, big circle. You can see a picture of it there. What else? What is important about a Ferris wheel? You don't have to write any of this down, by the way, if I start writing stuff. Like, what would make, one Ferris wheel different from another? Okay. What else? Sarah? The size, what do you mean by size? Yeah, so how would you measure the size? Like, how do you think about the size? Ah, nice. Radius, because it's a circle. That's a good term. Okay, anything else? How else would you describe the size? Radius and diameter, yep, exactly. Very good. Number of cars would be a different way of measuring size. Circumference, good, yeah. So that's like the distance around. That's interesting. So if you're picturing a person sitting in one of the cars, when they go around once, they would have gone around the circumference. What else? There's something I think about, like the size of one of these that would be important. Another way of thinking about it. Okay, yeah, the speed. So the spin direction and the speed. How would you measure, how would you measure speed? How would you think about it? Or anybody? Like, do you literally think the speed of the car? Is that how, what do you think?
Like how many times the car will pass a certain point in a certain amount of time?
Yeah, that's another way to think about it. Okay, so the speed of the car, like in kilometers per hour or meters per second. But the other way is the number of revolutions per minute. That's another way of thinking about speed, but they would be measuring the same speed. So just two different ways of thinking about it. If you don't know, like, do you picture Ferris wheels going fast or slow in general? Slow. Yeah, slow. It's not like a roller coaster, but maybe there are some that are faster. And I don't know. What else? Anybody have anything else? The height. So that's another way. That's what I was thinking too. Another way of thinking about the size is the height. So I was I looked this up, and the tallest in the world is called the High Roller, and it's in Vegas, New Vegas in the States. And I don't think it's been open very long, a few years, something like that. And there's another one that's being built in, I'm kind of making this up, at Singapore maybe or something like that, like somewhere on the other side of the planet. And it's being proposed to be built taller than this one. So if that happens, this one won't be the tallest anymore. But it is approximately 168 meters tall. It's pretty tall. The CN Tower is like 550 meters. So it's nowhere near the CN Tower if you've ever seen the CN Tower. CN Tower is really tall. But 168 meters, would be pretty tall. So if you were at the very top, you'd be able to see a long way. That's 550 feet. Pretty tall. Anything else that's important about a Ferris wheel? So the height, if a Ferris wheel had a diameter, let's say of 100 meters, so that would be a very tall one, what would its maximum height be? So if it had a diameter of 100 meters, what would the radius be? 50, because the radius is the distance from the middle to the outside. And then the diameter is the distance all the way through. So if that was 100, your maximum height would be a little bit more than that, right? Because it wouldn't be like directly on the ground. There would be a bit of a distance there. Does that make sense? See what I'm saying? So then the last thing that you might think about is this radius would be 50. So where would the center of the Ferris wheel be? Not at 50, because that means it would hit the ground when it came through. So what do you think? I mean, I have no idea how tall, but would it maybe be 55 meters? Like it maybe be like on a platform 5 meters up, you walk up and get on the chair at the bottom and then ride around. Would that be reasonable? Something like that? Okay, so you would have a gap at the bottom. The middle would be a little bit more than the radius, or a lot more, like I have no idea, depending on which one you're talking about. And then it would go up. So then what would the maximum height be if it was 5 meters off the ground? 105. Okay, interesting. And the minimum height would be 5. So this one would go from 5 to 105. 100 is the distance between them, and 50 would be the radius. These are just ways that you might think about a Ferris wheel. Oh, the high roller. Oh, I can't remember how much it cost. Maybe I'll look it up after. It was really expensive. Like, I want to say hundreds of dollars or maybe even $1,000 or something. Maybe not that much. Probably not that much. But it was really expensive. And you buy a ticket. You only go around once, but it takes 30 minutes. So that one would be very slow. But I think the point isn't that it's like a thrill ride. It's that you go up really high and you can see really far, that kind of thing. But some of them that are a lot shorter, you'd go around a bunch of times, I think. Okay, so here's what's interesting. Here's our Ferris wheel, okay? And that little black dot at the bottom is the rider, okay? When I drag, so this person, maybe it's you, is going to go around twice. Okay, just watch. Once, twice. Easy enough. If we were graphing this, so I'm graphing this person's height over time. This is 2 minutes long. So as we said, number of revolutions per minute. Watch, in 1 minute, right now it's at 1 revolution. So after a minute, they're back to their same position. And then after the second minute, they're back to their same position again. Okay, so we're going to graph 2 minutes, 120 seconds. What would the graph look like? Can anybody picture that? So the height over time. Sarah, what do you think? Good. Zach, what were you going to say? Same idea. So imagine you're starting at the bottom. Time goes forward, right? The dot goes backwards because it's going around the Ferris wheel. But a graph, time always moves forwards. So as time moves forwards, the person's going to get higher and then lower. And at 1 minute, they're going to be back to that minimum position and then back up again and then back down again. Okay, so I can actually turn this on. Let's try it. Now this is the same height as the rider. Goes up gets to the top at 30 seconds. You can see that works out. Down to the bottom at a minute. Back up to the top after another 30 seconds. That's 90 seconds total, 60 seconds and 30 seconds. And then back to the bottom. And remember what we talked about? The speed is like how many revolutions do we get in a minute. So this is 1 revolution in a minute. What else was important? The height. So there's your maximum height, which has that gap. And the middle is somewhere around there. I don't know where it is. Okay, height, which is the whole diameter of the Ferris wheel plus that little gap at the bottom. Now, we can change these properties with this little applet that we have in front of us. So what should I change? Do you want, I can't make it, it's as tall as it can get, so I'll make it shorter. The height right now is 16. Somebody shout out a number less than 16. What do you want me to make it? Thank you. So I'm going to shrink this down. And how many, right now it's at 1 revolution in a minute. How many do you want it to be? 4. How is this going to change the graph? You can picture that. So it's going to do 4 revolutions in 1 minute. So now it's gone through up and down 4 times in 1 minute. And then obviously if I go to 2 minutes, it'll be 8 times. And the peaks are a lot shorter. Again, if I increase the height, it increases the height of those peaks. But it doesn't change how wide they are, I guess you might call that. Now the last thing that we can do is I can actually do 2 of these at the same time. So right now the blue one is back to 16 and I'll put it back to 1. The red one's at 8. What speed should we have the red one at? 8? So then we can compare both of them. So they're going in the same amount of time, but the blue one only went once, and the red one went 8 times, and it's shorter versus the blue one that's taller. And I could switch these, so I could make this one down to a half, and I'll make this one, I don't know, 3. So if it's at a half, what does that mean? That means after a minute, it's only done half a revolution. The other one, the big one, has done 3. And then in the second minute, it completes the 1 revolution. So these are very different graphs. This is what we're going to study in this unit. And today we're not actually going to get to this graph, although we're going to see one that looks like it. We're just going to talk about these things called periodic functions in general. A periodic function, we're going to write this down, don't worry, but a periodic function is one that has a pattern that repeats over and over and over and over and over again. So most of the functions that you've seen so far are things like a parabola, a quadratic, right? You know what that looks like, or a straight line, something like that. And a parabola, if I cover this graph up, that top part of the blue thing kind of looks like a parabola, but a parabola would keep going down forever and ever and ever, whereas this one turns and goes back up and then repeats. And believe it or not, I don't know if you remember this last week, or even a while ago when I said we're doing 2 trig units. So this is the second trig unit. So what's very interesting is when in grade 10 and then so far in grade 11, when you've done trigonometry, sine and cosine and tangent, and you've done them in triangles, that blue curve, well, both of those are actually a graph of cosine. That's what cosine looks like as a graph. So that's what we're going to be studying in this unit, kind of a graph of sine and cosine, in particular tangent. Maybe we'll look at it once, but we're not going to do tangent too much. Tangent's very different. Sine and cosine are very similar to each other. That's the graph of sine. You probably wouldn't have expected that. But they can model all kinds of different situations. There's all kind. Can you think of anything else in the world? So a Ferris wheel, the height of a person, a rider, or something on a Ferris wheel is periodic because they go up and then back down, and then it repeats as many times as they go around the Ferris wheel. What else is something in life that repeats like that? A car wheel, so like the height of a position on a car wheel, yeah, or any wheel for that matter, right? Yep, absolutely. You think of anything else that cycles? Very good. So and there's different ways of measuring that. The height of the sun in the sky, or the amount of light throughout the day, that like the brightness kind of thing. Yep. What else cycles? Similar to the day, there's other things that cycle. Clocks, yep, for sure. The moon, the cycle of the moon, like going from a new moon to a full moon, that thing, right? Another famous application of this is the amount of light over the course of a year. So we all know that in the summer, the days are longer. There's more sun. The sun's out longer. Here, the rest of the planet is different, right? But for us in the summer, in July, the days are longer. And right now, I'm sure you notice, every day you wake up, it's like darker and darker and darker. Like it really changes fast at this time of year. And then we get into the middle of December or near the end of December when the days are the shortest. There's the least amount of sunlight. So that actually follows this kind of a curve. So like I said, we're not going to get to those yet. We're going to just talk about periodic functions in general today and some of the applications. But remember what we talked about. The whole point of looking at this graph and thinking about this is how the height, the maximum height, the minimum height, the total distance between the max and the min, how long it takes to complete one pattern, those are the important properties of these graphs. Another thing you might say is, I think usually for a Ferris wheel, you get on at the bottom, right? This is the easiest way to build one. But you could imagine a Ferris wheel that's built off of, I don't know, a cliff or like off of a bridge, or just has a really a lot of stairs or an elevator or something to get up, and you could get on at the middle and it would take you down. That might be kind of interesting to go like down the side of a cliff or something. Or you could even get on at the top and it takes you down to the bottom and brings you back up to the top. Like you could imagine somebody building a Ferris wheel like that. And then how would that change the graph? Instead of starting at the bottom here, you would maybe start at the middle, but otherwise the graph would look the same. Does that make sense? So those are the important properties of these graphs. Sort of how big it is, how many ups and downs you would get in a certain space, and sort of where it starts. All right, so your handout looks like this. Let's get to it. And there is a bunch of new terminology. That's one of the things that you're going to need to sort of learn and get used to, the words we use when we're talking about these special kinds of graphs that are periodic graphs. Okay, so one of them is a cycle, and a cycle is like one pattern. So for the Ferris wheel, it would be when you start at the bottom and you go around once back to the bottom. That would be one cycle of the graph of the periodic function. Okay. A period is the length of one cycle. So the period of a graph, if I go back to our applet, and if I just look at this one, the period of this is 20 because it goes from 0, it goes all the way up and all the way down in 20 seconds. So the period would be 20 seconds. And I can show that's one cycle. There's 2 cycles, and as we said, this was 3 cycles in a minute, and the length of each period is 20. So if I change the number of cycles that I can fit, I'm actually changing the length of a period of the graph. Okay. The amplitude is half the distance from the minimum to the maximum. You can, or it's the distance from the middle of the graph, if you can find the middle of the graph, to the top. So again, the actual maximum height, remember, is the entire, for this one, is the entire diameter of the Ferris wheel plus that little bit on the bottom. But the amplitude of the graph of a periodic function is, if I take the minimum value to the maximum value, whatever that is, which in this case is 16, right? Because we made it that way. But then you divide it by 2. So it's 8. For this graph, the amplitude would be 8. Actually, the amplitude I think the maximum is more than that. So I think the amplitude actually is 16 for this one. And it would be 32 from the very bottom to the very top. Twice the amplitude. And the amplitude is also the radius, let's say, of the Ferris wheel, right? Wherever the middle of this circle is to the top and the middle to the bottom would be the same distance. And again, we sort of talked about that. So this 50 is the radius. So that is the amplitude. And then the phase shift is like where in the pattern it starts. Oops. Now we're not really going to talk about phase shift today. It's going to come up. It's going to come up sort of starting tomorrow or later this week, because the phase shift only makes sense to talk about relative to a defined function like the sine curve and the cosine curve that we're going to look at. The ones we look at today are kind of just pictures of graphs. Okay, but that's what the phase of a graph is kind of like where in the pattern does it start. I get used to using these words. We're going to use them a lot, but if I ever use them and you don't know what they mean, feel free to ask, like, oh yeah, what's the amplitude again, or what's the period again, that sort of thing. So if we look at this graph, and if I think of this, whoops, I was going to do red so it stands out. Here's the start, and here's the end of one cycle. How many cycles are on this graph? Because it goes up, and then down, and then up higher, and then down, and then repeats. Up, down, up higher, down, and then repeats again, up, down, up higher, down, and then the next one goes off the graph. So we can see 3 full cycles of this graph in this picture. So the length of one cycle, there's one cycle, and its length, or its period, the length of that cycle is 4. 1, 2, 3, 4, because it starts at 0 and goes to 4. So this one in particular goes from 0 to 4. So it has a length or period of 4. But the whole point of periodic functions or periodic graphs is they keep going forever, right? So we can imagine this cycle repeating over and over and over and over and over again. But it will never go higher than that point and will never go lower than that point because the pattern will continue to repeat. So we kind of know what this graph will continue to do forever, forever, forever. So it has a max of 10 and a min of 0. And so the amplitude is half the distance from the max to the min. So what's it going to be? Probably just do this in your head. It's going to be 5. But if it was harder numbers, these are friendly numbers. If it was harder numbers, how would I calculate it? I would do the max minus the min, and you want to do it in that order, otherwise you're going to get a negative value, divided by 2. And it's always positive. The amplitude is a length, so it's like a size, so it's always positive. So 10 minus 0 divided by 2 is 10 divided by 2, which is 5. And again, remember what I said, it's also the distance from the middle to the top. So notice that that distance is 5, and that distance is 5. I take the amplitude twice, and that will get me from the minimum to the maximum. And this middle line, when we get to sine curve starting tomorrow, we call this the 0 line. It's sort of the middle of the graph. So to me, again, the Ferris wheel, that's like where the center of the Ferris wheel would be, the circle. Any questions so far? Does it make sense? Is it weird? What do you think? The last thing we're going to do here, because something that we often talk about functions, describe them, what are they like, what are their properties like, is domain and range. So for domain, we're going to do it 2 different ways. And we're going to do the range. If I was talking about the domain of the entire periodic function, it goes on forever in both directions. So the full graph would be x is an element of the real numbers. X can be anything. But what's a little bit more interesting is if I just talk about the domain of one cycle. So if you remember this one, we can say starts at 0 and one cycle ends at 4. So the range would be from 0 to 4. But just watch for a minute. What if I decided to start the period here, or start the cycle here? Then my domain would have been from 1 to 5. It would have still had length of 4, but because I started it at a different place, it finishes at a different place. Or I could start it here at 3, and then it's going to go up to 7. So it still has a length of 4. The period doesn't change, just where I'm thinking about the start changes. Does that make sense? So if you were doing domain of one cycle, you have to make sure you pick wherever you want to start it. If there's a clear starting at 0, you might pick that, right? But pick a clear place that starts. Make sure you go through one full pattern, one full cycle, and get to the same height. And then that's one cycle length, and you could use that for your domain. Notice that just because I go back to the same height doesn't mean I've done a full cycle. Like if I start here at the bottom, or if I start here and I go up and down back to 0, I haven't repeated one full cycle. Yes, I'm back to 0, but there's still a new part of the picture, and it's not till there that this picture is like cut and paste repeating over and over. Does that make sense? All right, so this is one cycle. I hope that makes sense for the difference. And then the range is y is an element of the real numbers, and this one goes from 0 to 10. And when you think about your amplitude, you're thinking about the max and the min, and when you're thinking about the length of a cycle, the period, you're thinking about where it starts and where it stops. So domain and range is like very similar and related to amplitude, the maximum value, the minimum value, the length of a period, that sort of thing. It's sort of all talking about the same thing, the properties of these periodic functions. Any questions before we move on? All right, so let's try a couple of these. We've got a few different graphs. For each of the following, determine period, amplitude, domain of one cycle, and range. And everybody's going to be different, I think. if you're looking at this picture, where does it, like, do you think a good place to start would be? Where would you start this graph? You might start at 0. It doesn't have to. Sometimes it might make sense, sometimes it might not. But you want to pick a clear place that has a good point and where it repeats to. So for example, you could start this one at 0 and it repeats there. So it's got this little flat part, and then it goes up, down part way, and then down at a different angle, and then that's when it repeats